A dense fog blankets the street, swallowing sound and light, as if the world has paused its breath. On a cold, moonless night, you step onto the road, unaware of the headlights slicing through the mist. A car surges forward, too fast, too close. Your heart lurches. But before impact, a stranger's hands shoves you aside. You stumble, safe, as tires screech and a body collapses onto the tarmac. An elderly figure, crumpled and still, has traded their life for yours. Later, in the quiet of a police station, an officer hands you an envelope, its edges worn, addressed to you in unfamiliar script. Inside, a note, just 2 words. Study physics. Who wrote it? Why did they save you? The mystery clings like the fog, pulling you toward a life reshaped by those words, toward a destiny entwined with the enigma of time itself. That night lingers, a wound and a gift, as you dedicate yourself to physics, chasing the secrets of the universe. Decades pass, and you stand celebrated, a professor unraveling Albert Einstein's theories of relativity. Time, you learn, is not a straight line but a fabric, woven with possibilities that defy intuition. Your obsession narrows to one question: can we travel through time? In your laboratory, surrounded by humming machines and scribbled equations, you crack it. The world's first time machine glows before you, its soft buzz a siren call. And then, clarity strikes like lightning. You pull the framed note from your wall, the one you've kept all these years, and slip it back into its envelope. Stepping into the machine, you set the dials to that misty night, knowing what you must do. You arrive just in time to push your younger self from the car's path, feeling the impact as the world fades. Your life ends where it was saved. But who wrote the note? It's a question that haunts, a paradox with no clear answer. You carried it back, but you received it first. It exists, creatorless, caught in a loop, a relic that seems to defy origin. This is the bootstrap paradox, a riddle where an object or idea circles through time, its beginning lost in the endless cycle. Did you choose to study physics, or was it always destined? The note's command feels like a whisper from nowhere, a thought born without a thinker. This is the ex nihilo paradox, where ideas emerge without a source. And what of your choice to step into the machine? If you hadn't, you'd have died young, never reaching this moment. Your path seems fixed, unchangeable, a thread in a tapestry already woven. This is the predestination paradox, suggesting your free will is an illusion, your future as set as the past. Imagine time as a river, vast and unyielding, carrying us from the Big Bang's foothills to the universe's distant end. We drift downstream, unable to paddle back or speed forward. Yet the river's source and mouth exist together, unchanging. Yesterday doesn't vanish, just as the riverbed doesn't dissolve behind us. Tomorrow isn't conjured from nothing. It's already there, as real as today. This is the block universe, a concept rooted in Einstein's work, where past, present, and future coexist in a single, four-dimensional tapestry. Your great-grandparents laugh upstream. Your descendants dream downstream, all as real as you are now. This idea, called Eternalism, clashes with presentism, the belief that only the present exists, the past gone and the future unborn. Philosophers have wrestled with this since ancient times, but Einstein's relativity gives eternalism weight, painting time as a landscape we traverse, not a fleeting moment. Picture yourself in a canoe, gliding through a jungle river, howler monkeys calling from the trees. The current pulls you forward, no effort needed, but you can't turn back. This is how time feels, relentless, unidirectional, Yet the river's upper reaches don't disappear just because you've passed them. They're still there, out of sight. Similarly, the block universe suggests the past endures, not as memory, but as reality. Einstein's special relativity, published in 1905, shattered the idea of absolute time. There's no universal clock ticking the same for all. Time bends, stretches, depending on how you move through space. One person's now can be another's then. Events shuffling like cards depending on your perspective. If my yesterday is your tomorrow, how can the past simply vanish? It must persist, woven into the fabric of space-time. Space-time, a term coined by Hermann Minkowski in 1908, unites space and time into one entity. Imagine it as a vast sheet stretching across the cosmos, where every event, your birth, your first kiss, your final breath, has a place, marked by 3 spatial coordinates and 1 temporal. A stationary object's mark moves only through time, second by second, tracing a line through this block universe. This line, your world line, maps your journey from cradle to grave. Every particle in your body follows its own world line, weaving together to form you, a knot in space-time's fabric. As you eat, breathe, or age, new particles join, others depart. But your path is fixed, unchangeable. The block universe is like a novel, its pages written, your choices already inked. You can't stray from the plot, just as a train can't leap its tracks. Now consider the paradoxes again. If you're destined to invent the time machine to save your younger self, where does the cycle begin? The letter loops endlessly, but does it age, growing tattered with each pass? This is the restoration paradox, questioning whether objects in a time loop degrade or endure, and what if you hesitate? Could you refuse to step into the machine, letting your younger self die? Logic falters here. If you don't save yourself, you'd never reach this moment to refuse. This is the autoinfanticide paradox, suggesting you can't undo your own existence. These riddles twist the mind, revealing time's complexity. The block universe, with its fixed paths, implies a destiny we can't escape. Yet the idea of looping back to rewrite our story tantalizes, a promise of control over the uncontrollable. Einstein's general relativity, unveiled in 1915, deepened this vision. It describes gravity not as a force, but as space-time's curvature. Picture space-time as a trampoline, sagging under the sun's weight, forming a gravity well. Planets roll through this dip, their paths curved by the fabric's shape. Mercury, closest to the sun, feels this curvature most, its orbit wobbling in ways Newton's laws couldn't explain. In 1859, astronomer Urbain Le Verrier puzzled over Mercury's odd path, suspecting a hidden planet. None was found. Einstein's equations solved the mystery, showing how space-time's curve, not a new planet, caused Mercury's precession. This triumph, announced in a letter to David Hilbert, proved general relativity's power, revealing gravity as geometry, not a pull. Space-time bends, and we move with it, our world lines tracing paths through a universe where all moments coexist. Tests of relativity multiplied. During a 1919 solar eclipse, light from distant stars bent as it passed the sun, confirming space-time's malleability. Gravitational waves, ripples in this fabric, were detected in 2015, further proving Einstein's vision. Black holes, swirling vortexes of curved space-time, bend light and time alike. These discoveries paint a cosmos where past, present, and future sit side by side, a block universe where every event is eternal. But if time is a river and we can't paddle upstream, how do we visit the past? The block universe suggests it's there, as real as now, but reaching it demands bending space-time itself. Your time machine, born from years of study, is the key, but its use raises questions. Did you choose to build it, or was it always meant to be? As you stand before your machine, the note in your pocket, the weight of that misty night presses close. You've lived a life shaped by a stranger's sacrifice, driven by 2 scrawled words. Now, you understand the stranger was you, older, returning to close the loop, but the paradoxes linger. Who authored your path? Was it ever yours to choose? The block universe holds your story. Every moment fixed, yet the possibility of stepping into the machine, of rewriting a moment, feels like freedom. The river of time flows on, carrying you toward a destiny already written. Yet the chance to loop back, to touch the past, whispers of a universe where endings are beginnings. As you set the dials, the hum of the machine fills the air, and the fog of that long-ago night seems to rise again, waiting for you to step through. The hum of the time machine fades, but its echo lingers in your bones, a reminder of the night you stepped through time to save yourself. Now, standing in the quiet of your laboratory, you wonder, can you truly outrun time, or are you merely chasing its shadow? The block universe holds every moment past, present, future, like stars fixed in a cosmic tapestry. Yet the urge to leap forward, to glimpse tomorrow, burns bright. What would it mean to visit the future, to see the world beyond your years? The river of time carries you forward, its current relentless, like a canoe gliding through a jungle's humid embrace. Howler monkeys calling from distant trees. You can't paddle back, but what if you could speed ahead, skipping decades like stones across water? The idea feels intoxicating, a chance to witness your descendants' lives or the universe's far-off chapters. Einstein's theories, the ones you've spent your life unraveling, suggest it's possible. Special relativity, born in 1905, reshapes time itself. It tells us there's no universal clock, no single now shared by all. Time stretches, contracts, depending on how fast you move through space. A traveler racing near light speed spends less time in motion, as if hoarding seconds while the world ages swiftly. This is relativistic time dilation, a key to the future. Picture a particle, a muon, born high in Earth's atmosphere, sparked by a cosmic ray's violent collision. These muons, unstable flecks of existence, should decay in a mere 1.56 millionths of a second. Racing at 98% of light speed, they plummet toward the ground. Yet far more reach it than should. Why time slows for them? From their perspective, fewer half-lives pass, as if they're cheating decay itself. In 1938, physicist Bruno Rossi, high in the Rockies at Echo Lake, measured these muons. His instruments, perched 2,300 meters above sea level, captured their strange survival. The muons were time travelers, skipping forward in a way that Rossi's calculations confirmed. Their journey, fleeting yet profound, proved that time bends for those who move fast enough. Imagine yourself as that muon, not falling to Earth, but looping through the cosmos at near-light speed. You embark on a 25-year journey, your spacecraft a speck against the stars. When you return, you're 25 years older, but Earth has aged 125 years. Your friends, your family, are gone, replaced by their grandchildren's grandchildren. The world you knew is a memory, its skyline reshaped, its stories faded. This is no paradox but a fact, woven into relativity's fabric. Time dilation doesn't just bend time, it reshapes lives. Consider the Kelly twins, NASA astronauts, Mark and Scott, born 6 minutes apart. Scott, spending months aboard the International Space Station, moved faster through space-time than Mark. Those extra days in orbit at speeds dwarfing a car's. Stretched time's flow. Mark, earthbound, aged fractionally more. By their reunion, Mark was 6 minutes and 5 milliseconds older, a gap widened by time's malleability. This effect, though small for astronauts, grows vast at extreme speeds. A traveler at 99.99% of light speed would weigh as much as a rhinoceros, their mass swelling with energy, as Einstein's equation energy equals mass times the speed of light squared reveals. Accelerating them would demand the energy of entire nations, a feat far beyond our grasp today. Yet, even on Earth, time dilation whispers its presence. Climb a mountain, like Rossi did, and you edge out of Earth's gravity well, where space-time is less curved. Time ticks slightly faster there. Atomic clocks, precise to a 15 billionth of a second per year, prove it. In 2022, physicists placed 2 such clocks a mere millimeter apart in height. The higher clock ran faster, its ticks outpacing the lower, confirming gravitational time dilation. Time, it seems, is not just relative to speed, but to gravity's pull. Gravity warps space-time, bending it like a sheet under a heavy stone. Near a massive object, like the Sun, space-time curves deeply, forming a gravity well. Planets trace paths through this dip, their orbits shaped by its contours. Mercury, plunging closest to the Sun, feels this curvature most, its path wobbling in ways Newton's gravity couldn't predict. In 1859, Urbain Le Verrier puzzled over this, suspecting a hidden planet. None was found. Einstein's General Relativity, published in 1915, solved the riddle. In a letter to David Hilbert, Einstein wrote of deriving Mercury's perihelion motion, a triumph no other theory had achieved. The Sun's gravity well, curving space-time, caused Mercury's orbit to precess, proving gravity is not a force, but a geometric dance. This curvature offers another path to the future. Enter a deep gravity well, like that of a supermassive black hole, and time slows for you. Spend a year near its edge, carefully avoiding its pull, and return to find Earth centuries older. This idea, explored in the film Interstellar, hinges on general relativity's truth. Space-time's shape dictates time's flow. Even on Earth, GPS satellites feel this. Orbiting high above, they move faster and sit in a shallower gravity well than we do. Their atomic clocks, ticking at a different rate, must be adjusted to sync with ours. Without this correction, your phone's navigation would falter, lost in time's subtle shifts. These experiments, Muons astronauts, clocks confirm time travel to the future is real, a scientific fact woven into the universe's fabric. But what drives this possibility? The block universe, where all moments coexist, suggests the future is already there, waiting. Your world line, the path you trace through space-time, stretches from birth to death, every choice mapped out. If you could leap forward, you'd land on a page already written, your descendants as real as you are now. The block universe, born from Einstein's relativity, paints time as a landscape, not a fleeting moment. Philosophers call this eternalism, opposing presentism's claim that only now exists. Eternalism sees your great-grandchildren living downstream, as vivid as your ancestors upstream. Time travel to the future, then, is less about creating tomorrow than visiting it, stepping into a moment already etched in space-time's block. Yet, the human cost lingers. To leap forward, you'd leave behind all you know. Imagine returning to a world where your loved ones are dust, their stories faded into history's pages. Ken Liu's story, Memories of My Mother, captures this ache. where a time traveler's journey disrupts family ties, generations slipping out of sync. The future beckons, but it demands sacrifice. You'd need a vessel to rival a muon's speed or a black hole's gravity, feats that dwarf our technology. The energy to propel a human near light speed equals months of global consumption. A barrier as real as the stars. Still, the possibility hums, like your time machine, promising a glimpse of tomorrow's light. As you stand in your laboratory, the note from that misty night in your hand, you feel the weight of time's river. You've saved your younger self, closed the loop. But the future calls, a horizon both distant and near. The block universe holds it all: your past, your now, your yet to come, yet the urge to leap forward, to see what lies beyond, stirs within. The muons, the clocks, the stars all whisper it's possible. Time, bent by speed or gravity, can carry you to a world not yet born. But what would you find there? A new dawn, or a shadow of what you've left? The river flows on, its currents pulling you toward answers that lie just out of reach. In a universe where every moment waits, eternal and alive. The laboratory is silent, save for the faint hum of your time machine, its dials glowing like stars against the dark. You've glimpsed the future's promise, the way time bends under speed or gravity, carrying you to tomorrow's already written. But what of yesterday? Can you step back, not just to save yourself, but to touch the past, to rewrite a moment lost in the river of time? The block universe holds every instant your first breath, a forgotten laugh, the night you were saved etched in space-time's eternal fabric. If the future is reachable, why not the past? The river of time, vast and unyielding, seems to flow one way, carrying you from the Big Bang spark to the universe's quiet end. Yet the past doesn't vanish, just as the river's source remains, hidden beyond the bend. Einstein's Relativity, the foundation of your life's work, suggests the past is as real as now, a place you might visit if you could bend the rules of space-time. But how the future yields to speed or gravity's pull. But the past demands something more, a way to tilt the river backward, to paddle upstream against its relentless current. In 1937, a young Dutch physicist, Willem Jacob van Stockum, peered into this possibility. His paper, dryly titled "The Gravitational Field of a Distribution of Particles Rotating About an Axis of Symmetry," hid a revolutionary idea: Einstein's equations. He showed allow closed timelike curves, paths through spacetime that loop back, letting your world line, the thread of your existence, intersect itself at an earlier point. A pensioner could revisit their childhood, or you could return to that misty night, pushing your younger self from harm. On paper, nothing in general relativity forbids this. Your time machine, buzzing in the laboratory, is proof it's possible. But Van Stockum's work hinted at a catch to loop back. You might need to travel faster than light, to step outside your light cone, the boundary of all paths you could take. Imagine standing still, your world line stretching forward through time. Light, racing at 300,000 kilometers per second, sets the limit of where you can go. 1 second from now, you can't be more than 300,000 kilometers away. 2 seconds, 600,000. This boundary forms your light cone, a funnel of possibility widening with time. To reach the past, your world line must curve back, crossing an earlier point. But to do so, you'd need to escape this cone, to move faster than light itself. Einstein's special relativity, born in 1905, declares this impossible. The faster you go, the heavier you become. Your mass, swelling with energy until accelerating further, demands an infinite force. Light speed is the cosmic wall, unbreakable for anything with mass. In 2011, a flicker of hope emerged. Physicists at the Opera experiment, buried beneath Italy's Gran Sasso mountain, announced a shock neutrinos, ghostly particles fired from CERN 730 kilometers away, seemed to arrive 60 nanoseconds too soon. If true, they'd traveled faster than light, shattering Einstein's barrier. The news rippled through the scientific world, promising a path to the past. A neutrino, moving faster than 300,000 kilometers per second, could tilt its world line back, looping through space-time. But by 2012, the dream faded. Faulty equipment, not superluminal speed, explained the anomaly. The light speed wall held firm, closing one door to the past. Yet other paths remained, hidden in space-time's folds. What if you could tilt your light cone without breaking light speed? In 1974, physicist Frank Tipler imagined a way. Picture a cylinder, 10 times the sun's mass, spinning billions of times a minute. Follow a precise spiral around it, and its immense gravity warps space-time, tilting your light cone backward. Your world line, confined within this cone, could loop to an earlier moment, carrying you to the past. Tipler's cylinder, though, was no practical machine. It needed to be infinitely long, a mathematical ideal far from reality. Even a finite version would require vast negative energy, a concept from quantum mechanics where empty space teems with virtual particles, briefly dipping energy below zero. These fleeting bursts, like an overdraft from the universe, couldn't sustain a human-sized time loop. The past, tantalizingly close, remained out of reach. Another possibility emerged, one that didn't demand impossible speeds or infinite cylinders. In 1985, Carl Sagan, crafting his novel Contact, sought a way to send a traveler to the star Vega, 25 light-years away, without breaking light speed. He called physicist Kip Thorne, who suggested a wormhole. Picture space-time as a sheet. Earth at one end, Vega at the other. Fold the sheet, bringing the points together, and a wormhole forms a tunnel through space-time's fabric. Step through, and you're at Vega instantly, without crossing the vast distance. From outside, it looks like faster-than-light travel, but you've merely taken a shortcut. Thorne realized wormholes could bridge time as well. Drag one mouth of a wormhole on a near-light-speed journey, and time dilation slows its clock. Return, and the mouths differ in age. Enter the younger mouth, exit the older, and you're in the past. But wormholes are fragile. Gravity from a passing object could snap them shut. To keep one open, you'd need negative energy again, or perhaps exotic forces like quantum entanglement or magnetic fields. In 1985, J. Richard Gott and William Hiscock explored cosmic strings, hypothetical threads of immense density left from the universe's birth. Tracing a precise path along two cosmic strings, you could tilt your light cone backward, looping to the past without exceeding light speed. Quantum entanglement, linking particles across vast distances, also hinted at superluminal connections. But transferring data or people this way proved impossible. Each path, cylinders, wormholes. Cosmic strings offered theoretical doors to the past, but none were practical. The block universe, with its fixed moments, seemed to taunt you, holding the past just beyond your grasp. Yet the past's allure persists. Imagine stepping through a wormhole, emerging on that misty night, not to save yourself, but to see your parents young, to walk streets long changed. The block universe says those moments exist, as real as now. Your world line, woven through space-time, could loop back. But the paradoxes loom. If you returned and changed the past, would you unravel your present? The bootstrap paradox. Your note. Circling without origin suggests a closed loop. But what if you refuse to write it? The predestination paradox whispers that you can't refuse. Your actions are fixed, written in Spacetime's book. The autoinfanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge free will itself. Was your choice to build the time machine ever yours? The river of time, with its eternal past and future, holds these questions. You've seen the future's possibility, confirmed by muons and clocks. The past, though, demands more a bending of spacetime's rules, a tilting of light cones. Van Stockham, Tipler, Thorne, and others map the path, but each requires feats beyond our reach. Infinite cylinders, stable wormholes, cosmic strings. Yet the block universe insists the past is there, waiting. As you stand before your machine, the note in your pocket, you feel the pull of yesterday. Could you step back, not just to close a loop, but to live a moment again? The river flows, its waters holding every memory, every regret. The hum of the machine grows louder, inviting you to chase the past, to seek answers in a universe where time, though fixed, whispers of possibilities yet untraveled. The laboratory air feels heavy, charged with the weight of questions unanswered. Your time machine, its soft glow, a beacon in the dim, hums with the promise of the past, a past you've touched once, saving yourself, but now yearn to explore further. What if you could rewrite a moment, undo a regret, only to find the universe splintering beneath your choice? The river of time, eternal and unyielding, holds every yesterday, but quantum whispers suggest its currents might fork, offering paths where paradoxes dissolve. The block universe, that vast tapestry of space-time where all moments coexist, paints the past as real as the present. You've seen how speed and gravity bend time, letting muons and astronauts slip into the future. The past, though, demands a steeper price, curving spacetime's fabric to tilt your light cone backward, looping your world line to an earlier day. Einstein's equations, your life study. Allow it through closed timelike curves, paths that circle back like the note you carried to that misty night. But the paradoxes, bootstrap, predestination, autoinfanticide haunt you. If you change the past, do you unravel your now? Quantum mechanics, the strange realm of the subatomic, offers a way out. A vision where time's river splits into countless streams, each a new reality. Picture yourself in a stark room, wrists bound by cold steel, sweat tracing paths down your face. Before you, a glass vial of lethal gas sits beside a hammer, its robotic arm linked to a machine measuring subatomic particles. Each particle can be in one of two states, A or B, a 50-50 chance. If it's A, you live. If B, the hammer falls, the vial shatters, and you die. The machine will measure 100 times before your release. The odds of surviving all 100 are 1 in a million trillion trillion, a number so vast it dwarfs the stars. Your heart pounds as the first measurement clicks. A, you breathe. The second, A again. By the 10th, hope flickers. By the 99th, you're dizzy with disbelief. The final click A, you're free, alive against impossible odds. This is no mere luck. It's a glimpse into the many worlds interpretation, a quantum theory that reshapes time's possibilities. In 1957, physicist Hugh Everett III proposed this idea: every quantum event with multiple outcomes splits the universe. When the machine measures A or B, reality fractures one world where you live, another where you die. After 100 measurements, 100 branches form, and in one, you survive, marveling at your fortune. In 99 others, you perish, each branch a different fate. This is the quantum immortality experiment, a human echo of Schrödinger's cat, where a feline in a box is both alive and dead until observed. Quantum mechanics says the particle exists in a superposition, both A and B, until measured. And so do you, alive and dead until the universe chooses. But Everett's many worlds theory says it doesn't choose. Every outcome happens, each in its own reality. This fracturing universe, a tree of infinite branches, offers a solution to time travel's paradoxes. Consider the grandfather paradox. You travel back. Kill your grandfather as a child, preventing your mother's birth, and thus your own. How? Then, are you here to kill him in the block universe with its fixed world lines? This seems impossible. Stephen Hawking's chronology. Protection conjecture argues the universe forbids such trips, guarding cause and effect. Igor Novikov's self-consistency principle agrees, saying you can visit the past but not change it, try to shoot your grandfather, and the gun jams, or you miss your actions, already written, can't rewrite the page. But these ideas falter in complex cases, like the one posed by physicists Barak Shoshani, Jared Wogan, and Jacob Hauser between 2020 and 2022. Imagine a time machine and a set of balls, each either black or white. When two balls meet, they swap colors. A black ball turns white, a white one black. A black ball enters the time machine, emerges in the past, and collides with its earlier self. The collision turns both balls white. The older ball, now white, loops back through the time machine again. But here's the paradox. The same ball exits the same machine at the same moment. Yet it's black the first time and white the second. Novikov's principle can't resolve this. How can the ball be two colors at once? The many worlds theory, though, offers clarity. The black ball starts in time stream A, emerges in time stream B, and collides with its past self. In this new stream, the other ball loops back, not the first. The paradox dissolves because the ball's journey spans different realities, not a single, contradictory loop. This idea frees you from the grandfather paradox. Travel back, kill your grandfather in time stream B, and your existence in time stream A remains untouched. Your mother, your birth, your life all safe in the original stream. Free will returns. You can choose without unraveling your past. The bootstrap paradox. 2 finds an answer. The note you carried to that misty night, seemingly authorless, might originate in another stream. In time stream A, you write it. Travel to time stream B and give it to your younger self. They, in turn, grow up, build the time machine, and carry the note to time stream C. The loop persists, but its origin lies across realities, not in a single, creatorless cycle. The ex nihilo paradox ideas like study physics appearing from nowhere fades as each stream provides a source, a writer in another world. But this solution carries weight. If every quantum event splits reality, the universe fractures endlessly. Every choice, every particle's flicker, spawns new streams. As physicist Bryce DeWitt said, every quantum transition in every star, every galaxy, splits our world into myriad copies. An infinite array of views, each slightly different. Lives every possible life, some where you're a poet, others a president, others never born. John Wheeler, who coined wormhole, grew wary of this, calling it laden with metaphysical baggage. Yet the many worlds theory gains followers. Its logic untangling time's knots. Your note, your machine, your choice to save yourself, they ripple across streams. Each reality a new verse in time's endless song. The block universe, with its fixed world lines, seems rigid, yet quantum mechanics suggests flexibility. Closed timelike curves, wormholes, cosmic strings all hint at paths to the past, but they demand exotic conditions, negative energy. Infinite cylinders, or stable tunnels through space-time. Quantum entanglement, linking particles across vast distances. Teases superluminal connections, but data can't travel that way. Still, the many worlds theory softens these barriers. If you step through a wormhole to the past, you emerge in a new stream, free to act without breaking your origin. The river of time, once a single flow, becomes a delta, its waters splitting into countless channels, each holding a different story. As you stand before your time machine, the note in your pocket feels heavier, its words a bridge between worlds. You've saved yourself once, closing a loop, but the past calls again, not just to repeat, but to explore. Could you visit a lost moment, see a loved one smile, without shattering your now? The many worlds theory whispers yes, offering a universe where every choice branches, where paradoxes dissolve into new realities. The laboratory's hum grows louder, the dials glowing with possibility. Time's river, vast and eternal, splits before you, its streams shimmering with lives unlived, moments unmade. You step closer, drawn to the promise of yesterday, wondering which world awaits your next leap. The glow of the time machine flickers in the laboratory, a silent witness to your journey through time's vast river. You've chased the future, glimpsed the past, and felt the universe splinter into countless streams, each holding a version of you. Now, standing at the edge of this moment, you wonder, what does it mean to live in a cosmos where every instant is eternal, where every choice echoes across realities? The note in your pocket, worn by years and loops, whispers the answer. Time is both your cage and your freedom. The block universe, that four-dimensional tapestry where past, present, and future coexist, holds your life's story, from the misty night you were saved to the hum of the machine before you. Einstein's Relativity, your life's work, reveals time as a landscape, not a fleeting moment. Your world line, the path tracing your existence, weaves through this landscape, fixed yet full of possibility. You've seen how speed and gravity stretch time, letting muons and astronauts slip into the future. You've explored paths to the past, closed timelike curves, wormholes, cosmic strings, each a theoretical bridge to yesterdays as real as now. The many worlds theory, with its branching realities, untangles paradoxes, letting you rewrite moments without unraveling your origin. But what does this mean for you? A knot of world lanes navigating an eternal cosmos. Picture the river of time, its currents carrying you from the Big Bang spark to the universe's distant end. You're in a canoe, gliding through a jungle's humid embrace, howler monkeys calling from unseen trees. The river's source, its bends, its estuary, all exist together, unchanging. Your great-grandparents laugh upstream. Your descendants dream downstream, each as vivid as you are now. This is Eternalism, the idea that all moments are equally real, opposing presentism's claim that only now exists. Philosophers like St. Augustine, in the 4th century, saw the present as a knife's edge between a lost past and an unborn future, but Einstein's general relativity, unveiled in 1915, paints a different picture. Time and space, woven into space-time, bend under gravity's weight, forming a block universe where every event, your birth, your choices, your end, is already written. Your world line, a thread in this tapestry, maps every step, from the breakfast you'll eat tomorrow to the day you'll marry. Every action is etched, unchangeable. The block universe is a book, its pages fixed, your choices pre-written. The note you carried back to that misty night, saving your younger self, was always part of the story. You didn't choose to study physics. The note, looping through time, ensured it. This is the predestination paradox, suggesting free will is an illusion. You built the time machine because you had to, because an older you already saved the younger, closing a loop that never began. The bootstrap paradox haunts you too, the note, creatorless, circles endlessly. Its origin lost in the river's flow, does it age, growing tattered with each loop. The restoration paradox asks this, while the autoinfanticide paradox insists you can't undo your own existence. These riddles, born from your journey, challenge the very notion of choice. Yet, the many worlds theory offers freedom. Each quantum event, each flicker of a particle, splits reality into streams. In one, you wrote the note. In another, you received it. In one, you saved yourself. In another, you hesitated. The grandfather paradox dissolves. You can kill your grandfather in a new stream, leaving your origin untouched. The ex nihilo paradox fades. The idea to study physics has a source across realities. Your time machine, buzzing before you, could carry you to a new stream where choices reshape outcomes. But this freedom comes at a cost. As physicist Bryce DeWitt said, every quantum transition in every star and galaxy splits our world into myriad copies. An infinite array of you's lives, every possible life, some triumphant, some tragic, some never born. John Wheeler, who named the wormhole, called this metaphysical baggage, yet its logic untangles time's knots. The river of time, once a single flow, becomes a delta, its waters branching into countless channels. You're not just a passenger, but a chorus of selves, each singing a different verse. Time travel to the future, proven by muons and atomic clocks, is a fact. Astronauts like Scott Kelly, aging fractionally less than his twin, confirm it. GPS satellites, ticking faster in Earth's shallow gravity well, rely on it. The past, though, is less certain. Closed timelike curves, like those Van Stockham proposed in 1937, allow it on paper. Wormholes, suggested by Kip Thorne for Carl Sagan's Contact, offer shortcuts through Spacetime's folded sheet. Cosmic strings, imagined by J. Richard Gott, tilt light cones backward, but each demands exotic conditions, negative energy, infinite structures, or stable tunnels beyond our grasp. Quantum mechanics, with its virtual particles and fleeting negative energy, hints at microscopic time loops, but scaling them for a human remains a dream. Still, the past feels close. You've touched it once, saving yourself, but the urge to return persists. Imagine stepping through a wormhole, not to that misty night, but to a quieter moment, a childhood afternoon. Your mother's laugh, a world before loss. The block universe says it's there, as real as now. But the paradoxes linger. If you change a moment, do you split the universe, creating a new stream? The many worlds theory says yes, freeing you to act without breaking your past. Yet, each action spawns new realities, an infinite cascade of yous. The note in your pocket, its ink faded, feels like a relic from another stream, a message from a self you'll never meet. Was it ever your choice to follow it, or was it written in the stars? Time travel, whether forward or back, reshapes not just moments, but meaning. To leap forward, you'd leave loved ones behind, as Ken Liu's Memories of My Mother shows, where a traveler's journey fractures family ties. To visit the past, you'd risk splintering reality. Each choice a new world. The block universe, with its fixed world lines, suggests you're a character in a finished book. Yet quantum mechanics offers a multiverse where every page branches. Your time machine, a bridge between these truths, hums with possibility. You've lived its proof, saving yourself, but the cost weighs heavy. Each trip, each loop, echoes across streams, reshaping who you are. The river of time, eternal and vast, holds every version of you, past, present, future, each a knot in spacetime's wave, unraveling and reforming with every choice. As you stand before the machine, its glow soft against the laboratory's shadows, you feel the river's pull. The note, tucked in your pocket, is both anchor and sail. You've traveled its loop, closed its circle, but the universe is wider now. Its streams infinite. Time travel, once a dream, is your reality. Yet it asks more than it answers. Are you free or fated? Do you write your story or merely read it? The block universe holds every moment, every you, in its embrace. The many worlds theory offers countless paths, each a life unlived. As the machine's hum fades, you step back. The note's words study physics echoing in your heart. Time's river flows on, its waters shimmering with every possibility, every regret, every hope, leaving you in awe of a cosmos where all moments, all selves, are eternal. There is something quietly wondrous aching, even in the way we look up at the night sky and feel both the intimacy of the stars and the infinite cold stretch between them. That gaze, born of awe, carries within it the seed of ambition, the deep, relentless desire to reach out, to touch what is immeasurably far, to fold the cosmos into something a little more human-shaped. We are wanderers confined to a cradle, dreamers on a pale blue dot spinning through darkness, imagining pathways across the stars. Yet for all our dreaming, the truth remains immutable and unforgiving. The universe is vast beyond reckoning. To journey to even our nearest galactic neighbor is to confront distances so immense they warp the meaning of time and distance itself. This is the frontier that awaits us, not just a technological challenge, but a redefinition of what it means to go anywhere at all. In this first step of our exploration, we must come to terms with the full magnitude of the journey. For in doing so, we begin to understand why our current engines, our methods, our assumptions must all be rewritten if we are ever to leave the quiet harbor of our Milky Way and sail the black ocean that lies beyond. To measure the universe is to enter a realm where numbers lose their emotional resonance. Light, the swiftest thing we know, takes over 8 minutes to reach us from the sun. That same light would take more than 4 years to reach Proxima Centauri, the nearest star beyond our own solar system. But the Andromeda Galaxy, the majestic swirl of starlight most visible from the northern hemisphere on a moonless autumn night, is 2.5 million light-years away. This means that the light reaching us now from Andromeda set out long before modern humans existed. That ancient shimmer, delicate and unwavering, is a message from a time before memory, from a place we can see but never touch, not with the means we have today. The distances involved in intergalactic travel defy imagination. If Earth were a grain of sand and the Sun stood a mere meter away, Andromeda would still lie over 250 kilometers down the road. Our fastest spacecraft, like Voyager 1, launched in 1977 and now coasting through interstellar space at about 17 kilometers per second, would take roughly 40,000 years just to reach that nearby star Proxima Centauri. To reach Andromeda at that speed, multiply that by over 60 million. These are not distances we traverse. They are cosmic gulfs that remind us how small, how local, our reach truly is. Our scientific curiosity, though insatiable, slams up against a wall, Einstein's wall. According to his theory of relativity, nothing with mass can ever reach or exceed the speed of light, approximately 300,000 kilometers per second. This isn't a technical limitation, it's a fundamental feature of the way the universe is stitched together. Time and space themselves bend and resist at those thresholds. As objects approach light speed, their mass increases asymptotically, requiring infinite energy to push just a little further. Time for the traveler slows to a crawl. The fabric of reality strains, but it does not yield. We are locked in a prison of speed, held captive by the very equations that describe the cosmos so elegantly. And so we are forced to ask a deeper question, not just how to move faster, but how to move differently. What if distance is not what we think it is? What if space can be bent, twisted, connected in ways our intuition doesn't allow? To begin contemplating intergalactic travel is to leave behind the comfort of rockets and propulsion systems, and to instead question the architecture of the universe itself. This is not science fiction, it is theoretical physics at its most adventurous. Einstein's own equations allow for the possibility that space is not a rigid stage, but a dynamic entity that can curve, ripple, and even loop back on itself. The notion of wormholes, hypothetical bridges through space-time, emerges from these same equations. These Einstein-Rosen bridges, as they were first called, offer an escape from the tyranny of distance. If 2 points in space can be connected through a higher dimensional tunnel, the traveler need not cross the space in between. Instead, one would step through a portal and emerge somewhere else, as if reality itself had been folded like a sheet of paper. The distance isn't conquered, it's bypassed entirely. It's as if the universe, though vast, contains hidden shortcuts, cracks in the fabric through which bold civilizations might one day slip. The idea is seductive, and it haunts the dreams of physicists and engineers alike. But dreams must bow to the brutal demands of reality, and wormholes, if they exist at all, pose immense challenges. To truly grapple with the scale of the problem, we must step back and consider just how far human ingenuity has taken us and how far we still have to go. Our journey to the moon, though historic, was a mere 384,000 kilometers. Our robotic explorers have reached every planet in the solar system, yet even they are but messages in bottles cast upon the tide. Voyager 1, now in interstellar space, has traveled over 24 billion kilometers in nearly 50 years, and yet, on the galactic map, it hasn't moved at all. This sobering truth reveals the inadequacy of our current technological paradigms. Chemical rockets, nuclear propulsion, even ion drives, each incrementally better, yet none sufficient to cross the sea between galaxies. It is not speed we lack. It is a new kind of motion altogether. We are like cave dwellers with torches, staring at the ocean and dreaming of stars, not yet understanding the need for ships or sails or the wind that might carry us forward. Andromeda is not just a distant object. It is a symbol of our longing. It is the lighthouse at the far end of possibility. The idea of reaching it forces us to rethink our place in the cosmos. It forces us to recognize that space is not empty. It is structured, dynamic, and potentially navigable in ways we are only beginning to imagine. In this light, wormholes are not just curiosities. They are provocations. They ask us whether the barriers we perceive are real or merely reflections of our current limitations. If we take Einstein seriously, and we must then, the universe might contain within it the seeds of its own traversal. But if such paths exist, they are not easy. They require conditions we do not yet know how to create or even detect. They may demand forms of energy we have not harnessed. They may require us to tame space-time itself. Yet the act of considering them transforms us. It stretches our thinking. It pushes the boundaries of what is knowable and, in doing so, what is possible. There is beauty in this confrontation with the impossible. There is something profoundly human in our refusal to be confined. The journey to Andromeda is not only a journey through space, it is a journey through knowledge, through patience, through time. Even if no ship ever sets sail, the act of imagining it reshapes our understanding of physics and reality. The cosmos does not promise us that travel between galaxies will ever be easy. But it does whisper in equations and quanta that perhaps it is not forbidden. And in the silence of space, where stars drift and galaxies turn in slow spirals, that whisper may be enough to begin. Wormholes, shortcuts through space-time. If the stars seem distant, it is not because we cannot see them, but because we cannot reach them not yet. Our minds, however, are not bound by this limitation. Long before our engines can challenge the cosmos, our equations already have. From the moment Einstein's theory of general relativity reshaped our conception of space and time from a static backdrop to a dynamic fabric, new possibilities emerged, some strange, others sublime, and among the most tantalizing wormholes, these hypothetical tunnels in space-time arise not from science fiction, but from the very heart of the mathematics that governs our universe. They are not fantasy, they are the offspring of logic and light. Wormholes suggest that maybe, just maybe, the great intergalactic gulfs that stretch across the sky might not be impassable after all. Maybe distance is not a wall, but a veil. And maybe, if we find the right path through space-time, we can slip through that veil in an instant. In this exploration, we leave behind the slow crawl of rockets and sail directly into the geometry of the cosmos, seeking the doors that may already exist in the structure of reality itself. The origin of the wormhole concept can be traced back to Einstein himself and to his collaborator Nathan Rosen, who in 1935 described what would become known as the Einstein-Rosen bridge. Their solution to Einstein's field equations illustrated how two black holes could be connected through a tunnel-like structure in the curvature of space-time. At first glance, this was a mathematical curiosity, an elegant artifact of the equations, but it carried profound implications. In theory, one could imagine a traveler entering the black hole on one side, navigating the bridge, and emerging elsewhere in the universe, or perhaps even in another universe altogether. The term wormhole was later coined in the 1950s by physicist John Wheeler, who helped bring this idea into the lexicon of modern theoretical physics. The metaphor was charmingly vivid. It imagined space as an apple, and a worm burrowing through it rather than crawling across its surface. The journey from point A to point B is drastically shortened, not by speed, but by topology. This analogy would prove enduring, not merely as an illustration, but as a conceptual map for physicists trying to grasp the nature of these theoretical shortcuts. To understand wormholes, one must first let go of the notion that space is flat, like a sheet of paper. General relativity teaches us that mass and energy bend space-time, curving it in ways that defy Euclidean geometry. Massive objects like stars and black holes warp the space-time around them, creating gravitational wells, a wormhole, in contrast, is not merely a dip in the sheet, it is a tunnel punched through it, connecting two distant locations with a bridge through higher dimensional space. Think of folding that paper in half and pushing a pencil through both layers. The path through the hole is far shorter than the path across the surface. In a universe where distances are measured in light years and energy flows along the fabric of time, such a structure would be revolutionary. It would render the speed of light irrelevant, not by breaking the cosmic limit, but by changing the very definition of distance itself. This is the core allure of wormholes. They promise a loophole, a graceful sidestep around the hardest constraint in the universe. But not all wormholes are created equal. The Einstein-Rosen bridge, elegant though it may be, suffers from a fatal flaw: it is non-traversable. Any attempt to pass through it would end in catastrophe. These bridges are unstable. They collapse too quickly for anything even light to pass from one end to the other. They are like shadows of possibility, tantalizing but out of reach. The tunnel pinches off before it can be crossed, a cosmic mirage. To create a traversable wormhole, one that a spaceship or message could actually use, requires something more exotic matter with negative energy density, or exotic matter. In simple terms, this means a form of energy that would resist the natural tendency of spacetime to snap closed. It would act like scaffolding, propping the throat of the wormhole open and keeping it stable. Without such a substance, the wormhole is nothing more than a beautiful trap, a doorway that collapses the moment we try to walk through. This brings us to a frontier of physics where theory trembles on the edge of the unknown. Negative energy is not an entirely alien concept. In quantum field theory, phenomena like the Casimir effect demonstrate that under certain conditions, energy densities can indeed dip below zero. In this effect, two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force due to quantum fluctuations, a whisper from the vacuum itself. This suggests that the vacuum is not empty, but rather a seething sea of virtual particles and fields. Within this sea, the temporary emergence of negative energy is not forbidden. It happens, but harnessing it, shaping it, and amplifying it to the scale required to stabilize a wormhole, that is an undertaking so far beyond our current capabilities that it borders on the miraculous. Exotic matter may be permitted by the laws of physics, but the laws of engineering have yet to catch up. Even if such matter could be generated or discovered, the challenges remain daunting. For a wormhole to be traversable by humans, it would need to have an opening wide enough to allow the passage of a spacecraft, and its internal geometry would need to be navigable without subjecting travelers to tidal forces so extreme they would be torn apart. Theoretical models have been proposed most notably by physicists Kip Thorne and Michael Morris in the 1980s that lay out the conditions for such wormholes. These so-called Morris-Thorne wormholes provide a blueprint, a space-time tunnel supported by a shell of negative energy that prevents collapse. They showed that, in principle, such structures could allow faster-than-light travel without violating relativity because no object actually moves faster than light within its own local frame. Instead, the distance is altered. The journey takes less time because the path is shorter, not because speed has increased. This subtle but profound distinction preserves the integrity of Einstein's laws while opening a door to the stars. Visualizing such a structure challenges the imagination. It's not a tunnel in three-dimensional space, but a region of four-dimensional space-time. To a traveler, the approach to a wormhole might look like a shimmering sphere or a rippling distortion, a place where stars warp and light bends strangely. As they cross the event horizon, the point of no return for traditional black holes, they would instead find themselves accelerating not toward destruction, but toward another region of space, perhaps even another galaxy. And yet, As wondrous as this vision is, it raises deeply troubling questions about causality and paradox. If wormholes allow faster-than-light travel, do they also permit backward time travel? Could signals sent through a wormhole arrive before they were sent? Would this violate causality, allowing paradoxes to proliferate and undermine the logical structure of the universe? Some physicists argue that quantum effects or instabilities would prevent such violations. Others suggest that the universe may be more permissive than we realize. The debate is not settled, it is alive, humming with speculation and hope and caution. The search for wormholes is not merely an academic exercise. Observational astronomy has begun to ask if these structures exist. Could we detect them? Might some of the gravitational lensing effects we observe, where the light from distant galaxies is bent and magnified, be caused not by ordinary matter, but by the warping effects of a wormhole? Could regions of space-time that appear to distort starlight in strange ways be the mouths of hidden tunnels? Some researchers have proposed that future space-based observatories, with greater sensitivity and angular resolution, might one day identify candidates. The detection of a traversable wormhole would be one of the most profound discoveries in human history, a confirmation that the universe not only contains distant worlds, but bridges to reach them. In contemplating wormholes, we also come face to face with the nature of reality itself. Are these structures real, or are they merely artifacts of our mathematical frameworks? Do they exist in the same way mountains exist, or in the way dreams do? The distinction matters, and yet the act of considering them changes how we see the universe. It transforms space from a void into a landscape, one that may be shaped, tunneled, and explored. This shift in perspective mirrors other revolutions in science, where the impossible becomes plausible, then practical. Once, heavier-than-air flight was fantasy. So was landing on the moon. If history teaches us anything, it is that the impossible is often a matter of timing. And still, beyond the physics, there is something profoundly human about the pursuit of wormholes. They speak to our desire not merely to move, but to belong, to be part of a cosmos in which connection is possible. Not just metaphorically, but physically. They embody the hope that no part of the universe is truly unreachable, that even in the silence between galaxies, there might be pathways hidden in the weave of space-time. In that hope lies the soul of exploration. Wormholes are not just scientific curiosities. They are symbols. They represent our refusal to be limited by what is, and our willingness to imagine what might be. They remind us that even in a universe bound by laws, the imagination can find freedom. And perhaps, one day, so will we. Exotic matter, energy barriers, and quantum limits. Every bold vision of interstellar passage through wormholes eventually collides with a barrier more implacable than any cosmic distance, the laws of physics themselves. And yet, within those laws, paradoxically, lie the seeds of possibility. If the idea of a wormhole is not itself forbidden, if space-time truly allows for such tunnels to exist, then the question becomes not one of conceptual legitimacy, but of material feasibility. What must the universe contain or permit us to create for these bridges between stars to remain open long enough to serve as conduits for matter, light, and thought? The answer, cryptic, evasive, and yet oddly compelling, centers on one of the most enigmatic substances ever theorized: exotic matter. Not simply rare or unfamiliar, but fundamentally alien to our experience. Exotic matter would possess negative energy density, behaving in ways no ordinary substance can. It would violate the so-called energy conditions that underpin general relativity assumptions that, in the everyday world, keep energy positive, mass attractive, and spacetime well-behaved. But to hold open the throat of a wormhole against the crushing weight of curved geometry, something must push back, and only exotic matter appears to have the power to do so. Yet invoking it is no mere footnote to theory. It invites us to the very edge of what is known and asks whether the cosmos contains material stranger than anything in our laboratories, or whether we must one day learn to manufacture them from the quantum vacuum itself. To understand why exotic matter is necessary, we must return to the geometry of wormholes as described in general relativity. Space-time, when curved into a wormhole, naturally wants to collapse the tunnel the same way a stretched rubber membrane recoils or a sand tunnel caves in under the weight of gravity. Einstein's field equations suggest that this collapse is inevitable unless something counteracts it specifically, unless some form of stress energy exists that exerts negative pressure. This is where the usual energy conditions like the null, weak, strong, and dominant energy conditions come into play. These mathematical constructs essentially state that energy density, as measured by any observer, should always be non-negative. Violating them leads to strange consequences, repulsive gravity, reversed cause and effect, and a breakdown of what we call normal physical behavior. Yet wormholes demand exactly such violations. In order to remain stable and traversable, a wormhole must have regions where the energy density is less than zero, where spacetime itself is propped open by an anti-gravitational force. Exotic matter, in this context, is not a luxury. It is the linchpin of the entire theoretical framework. But does such matter exist at macroscopic scales? We have never observed anything resembling it. Our entire experience of matter and energy is bounded by positivity. Mass attracts, energy builds, radiation flows outward. Nevertheless, hints from quantum theory suggest that negative energy, while rare and fragile, is not entirely forbidden. Enter the Casimir effect, one of the strangest consequences of quantum field theory. First predicted in 1948 and confirmed in laboratory experiments since. The Casimir effect arises when two uncharged conducting plates are placed extremely close together on the order of micrometers in a vacuum. According to quantum field theory, the vacuum is not empty, but filled with fluctuating fields that give rise to virtual particles. These particles momentarily pop into and out of existence, and their interactions give rise to a sea of energy even in what we call empty space. When the plates are introduced, they limit the wavelengths of the virtual particles that can exist between them compared to those outside. This asymmetry in vacuum energy density results in a tiny yet measurable attractive force that draws the plates together. In essence, the vacuum between the plates has less energy than the surrounding space. It behaves as if it contains negative energy. This real-world demonstration is subtle but profound. It suggests that nature, at its quantum foundations, does allow for local violations of energy conditions, at least temporarily, and at small scales. Scaling this phenomenon up to cosmic levels, however, is a challenge of monumental proportions. The energy differences in the Casimir effect are minuscule, barely sufficient to nudge lightweight plates, let alone keep open a tunnel through spacetime large enough for a spacecraft. To build or stabilize a traversable wormhole, we would need vast amounts of negative energy comparable to the mass energy of a star, or greater, depending on the size and geometry of the wormhole. Moreover, this negative energy must be confined and distributed in a precise manner, forming a kind of shell or halo around the wormhole's throat, without dispersing or collapsing under its own quantum instability. The technology to create, sustain, and control such configurations lies far beyond our current capabilities, not merely in engineering, but in our fundamental understanding of quantum fields and spacetime itself. There is, however, another thread of inquiry, one that probes even deeper into the structure of the universe and may offer both hope and warning. Quantum field theory not only permits negative energy, but also imposes limits on its use through constructs known as quantum inequalities. These inequalities, derived from rigorous mathematical analysis, place bounds on the magnitude and duration of negative energy that can exist in any given region. In simple terms, while quantum theory allows for dips below zero, it restricts how deep and how long these dips can last. The more intense the negative energy, the shorter the time it can persist. This has profound implications for wormhole stability. Even if exotic matter can be generated, quantum inequalities may ensure that it dissipates too quickly or fluctuates too wildly to provide the stable support required for a traversable structure. Some physicists interpret these limits as a kind of quantum censorship, a subtle mechanism by which the universe prevents large-scale violations of causality and chronology. Others believe that under special conditions, such as in curved spacetime or within certain quantum states, these limits might be loosened or bypassed. A particularly intriguing possibility arises from the interplay between quantum entanglement and geometry. In recent years, a deepening connection has been proposed between entangled particles and space-time topology captured in the evocative slogan ER equals EPR, proposed by physicists Leonard Susskind and Juan Maldacena. This idea suggests that the Einstein-Rosen ER bridge, or wormhole, and the Einstein-Podolsky-Rosen EPR paradox of quantum entanglement may be two sides of the same coin. In this framework, entangled particles might be connected by microscopic, non-traversable wormholes, tiny bridges of spacetime that reflect their inseparable quantum nature. Though these structures are far too small and fleeting to be useful for transport, they hint at a profound unity between the quantum and geometric realms. If entanglement can be interpreted as a kind of space-time connectivity, then perhaps under certain extreme conditions, such as in the vacuum near black holes or in high-energy particle interactions, this connectivity could be magnified or manipulated. Could vast, engineered, entangled states one day form the scaffolding for a macroscopic wormhole? The mathematics is speculative, but the direction is compelling. It suggests that wormhole physics may not be separate from quantum gravity, but rather an emergent property of it. Adding to this tapestry of speculation are attempts to simulate wormhole-like behavior in laboratory settings using analog systems. Physicists have begun to experiment with models in condensed matter physics, optics, and even superconducting circuits to mimic certain aspects of curved spacetime. These so-called analog gravity systems can create environments where light, sound, or other waves behave as if they are moving through a warped geometric medium. In 2022, a group of physicists even claimed to simulate the dynamics of a traversable wormhole using a quantum computer, based on a simplified model derived from the SYK Sachdev Yakitiev system. While this was not a physical wormhole, the simulation offered a glimpse into how information might traverse such a structure, preserving the basic principles of entanglement and causality. Though highly idealized and far removed from real-world travel, such simulations provide test beds for theory, allowing physicists to probe the strange consequences of exotic matter and quantum constraints without having to build wormholes themselves. They serve as rehearsal stages for a deeper play, one in which the actors are not stars and planets, but wave functions and probability amplitudes. Yet for all these hints and analogies, the fundamental question remains unanswered. Can exotic matter exist in sufficient quantities and in controllable forms to make wormholes not just imaginable, but real? The answer may lie at the intersection of quantum mechanics and general relativity, a realm still not fully understood. Any complete theory of quantum gravity, whether through string theory, loop quantum gravity, or another yet-to-be-discovered framework, must grapple with the implications of negative energy and energy condition violations. It must tell us whether these are tolerated glitches or foundational features of reality. In the meantime, wormhole theorists walk a fine line between hope and humility. They construct ever more refined models, analyze the stability of hypothetical geometries, and search for loopholes within the loopholes ways to skirt quantum inequalities, engineer stable configurations, or discover naturally occurring analogs in the universe's most extreme environments. There is poetic symmetry in the fact that the path to wormholes, the dream of bypassing the vastness of space, requires a plunge into the deepest, smallest realms of reality. To go far, we must go deep. To transcend distance, we must understand the vacuum. And in that vacuum, perhaps, lie the ghosts of possibility, negative energies, exotic pressures, entangled topologies, and space-time geometries unlike any we have ever encountered. The beauty of this search is that it does not merely expand our horizons outward, but inward. It reveals that even the emptiest regions of the cosmos are not voids, but theaters of quantum drama, seething with potential and paradox. Exotic matter is not just a hypothetical tool, it is a window into the most profound structures of being. Ultimately, the notion of wormhole travel is not just a challenge for engineering or theoretical physics. It is a philosophical reckoning with the very nature of connection, limitation, and aspiration. If we discover that wormholes can never be traversed, that the laws of quantum mechanics and energy prevent it utterly, then we will have learned something essential about the architecture of the cosmos. But if, on the other hand, we find that under specific, extreme, and careful conditions, these structures can exist and be stabilized, then the door opens not just between stars, but between epochs. We will stand on the edge of a second Copernican revolution, realizing that our place in the universe is not bound by proximity, but by understanding. And perhaps, in some distant future, when humanity has learned to sculpt quantum fields as effortlessly as we now sculpt stone or steel, a ship will one day slip into the throat of a wormhole, guided not by rockets, but by resonances in the vacuum, and emerge beneath another sky, light years away, carried there not by speed, but by knowledge. Competing concepts, time dilation, warp drives, and hypervelocity. Time, as we experience it, is steady, inescapable, and seemingly impartial. Yet Einstein taught us that this quiet river can bend, slow, and stretch depending on how fast we travel or how near we drift to gravity's heart. In our yearning to cross the oceanic void between stars and galaxies without the luxury of wormholes or shortcuts, our attention turns to space-bending ideas rooted in the very fabric of physics itself. One of the most tantalizing notions is that of time dilation, a relativistic phenomenon predicted by special relativity, where time slows down for an object as it approaches the speed of light. It means that if a spacecraft were to travel at 99.99% the speed of light, its crew might age only a few years while centuries pass on Earth. For interstellar travel, this presents a curious asymmetry. A round-trip voyage to Andromeda might feel brief to the traveler, but would strand them billions of years into Earth's future upon return. Thus, relativistic travel offers a potential bypass of the subjective experience of time without violating the cosmic speed limit itself, but it does not reduce the actual distance. Light years remain light years, and no matter how fast you go, the universe outside still ticks on, indifferent to your personal temporal illusion. Yet this mechanism still opens a philosophical window. Perhaps humanity could leave behind the burden of synchrony and embrace a future where explorers become true time travelers, journeying into the distant epochs of the cosmos, though never able to return to the time they left behind. But achieving such near-light speeds is no trivial feat. Our current spacecraft barely graze a fraction of this threshold, with Voyager 1 moving at a mere 17 kilometers per second, a paltry pace when compared to the velocities required to trigger meaningful time dilation. Even if we imagined propulsion systems capable of sustaining acceleration for years, the energy demands rise exponentially as one nears light speed, for a human-carrying spacecraft to approach zero. 9c, the speed where relativistic effects become pronounced, the energy cost is astronomical, comparable to the entire global output sustained over centuries. That doesn't even account for shielding against interstellar dust, which at such speeds could punch through metal like cosmic bullets. So, while time dilation is real and observable, confirmed in experiments with atomic clocks aboard jets and satellites, turning it into a usable technology for intergalactic journeys remains a bridge too far for now. But the universe, as always, provides us with clues. Take hypervelocity stars. For example, these stellar runaways, hurled from galactic centers through interactions with supermassive black holes, can reach speeds exceeding 1,000 kilometers per second, fast enough to eventually escape their home galaxies. These cosmic cannonballs are natural demonstrations of gravitational slingshots, and they hint at techniques we might someday use to accelerate probes or ships. Already, we use gravity assists to nudge our robotic emissaries Voyager, Galileo, Cassini toward the outer planets by dipping into a planet's gravitational well and swinging around it. A spacecraft can rob a bit of orbital momentum and slingshot itself forward. It's akin to a cosmic billiards trick, where the cue ball gains speed from every bounce. Could we string together a chain of such assists, perhaps bouncing around stars or even black holes, to reach relativistic speeds? In theory, yes, but in practice, the alignment of such celestial bodies and the precision required would render it a monumental coordination task. Still, the idea persists in theoretical papers and simulations as an elegant and energy-efficient way to accelerate without propulsion, letting gravity itself do the heavy lifting. Moreover, these hypervelocity stars inspire dreams of galactic pinball, where future spacecraft might dive into the wells of neutron stars or white dwarfs to catch gravity's wave and ride it across the stars. But even then, we remain shackled to light speed's asymptote, never reaching it, always expending more energy for less gain as we climb the relativistic curve. Enter then the warp drive not as a sci-fi trope, but as a legitimate, if speculative, solution proposed by physicist Miguel Alcubierre in 1994. His now famous paper described a way to move a spacecraft not through space but by deforming space itself. The Alcubierre drive envisions a warp bubble that contracts spacetime in front of a ship and expands it behind, allowing the vessel to ride a wave of spacetime distortion, effectively moving faster than light from an external observer's viewpoint without violating local physics. Inside the bubble, the ship remains stationary relative to its own pocket of spacetime, thereby dodging the relativistic penalties of conventional propulsion. It's a clever loophole. Spacetime itself isn't bound by the speed limit that governs mass and energy, and since general relativity permits the stretching and contracting of space, the idea remains mathematically consistent. However, there's a catch several. In fact, the original Alcubierre metric requires enormous amounts of negative energy, akin to exotic matter, to form and sustain the warp bubble. Estimates suggest that the energy equivalent of several Jupiter masses would be required just to move a small craft. More conservative revisions have since reduced this figure, but the fundamental challenge remains: where do we get this negative energy? and how do we stabilize the bubble? Additionally, the warp drive poses paradoxes of its own. As the ship emerges from the bubble, causality could be violated, possibly allowing for closed, timelike curves, essentially time travel to the past. That invites not only technological but philosophical conundrums. And then there are the stability issues. Simulations suggest that even small perturbations might collapse the bubble or fry the contents of the ship with a burst of radiation. Furthermore, the energy conditions required for the warp drive overlap closely with those demanded by traversable wormholes, suggesting a deep symmetry between these seemingly disparate ideas. Both require exotic matter. Both manipulate spacetime on a local scale to achieve non-local results, and both raise profound questions about energy conservation, quantum gravity, and the structure of the vacuum itself. In many ways, the warp drive is the cousin of the wormhole. One folds space like paper, connecting 2 points. The other surfs space like a wave, carrying a bubble through the ocean of the void. Neither is experimentally feasible, but both are logically allowed within the scaffolding of general relativity, provided we can bend the rules with enough ingenuity. Beyond these grand visions lie other, more incremental concepts. Ramjets that harvest interstellar hydrogen, nuclear pulse propulsion systems like Project Orion that use controlled atomic explosions to push ships forward, or solar sails that ride photon pressure from massive lasers. These methods don't reach light speed, but they inch us closer to the stars, and perhaps, as stepping stones, they will enable robotic scouts to precede us, building relays, factories, or way stations along the route to distant systems. Perhaps the future won't be one of singular breakthroughs, but of compounding innovations, small victories in material science, energy storage, and navigation that, like the Polynesians crossing the Pacific, allow us to leapfrog from world to world. It may be less romantic than wormholes or warp drives, but no less noble. After all, even the most fantastical visions must be scaffolded on reality. And sometimes, evolution trumps revolution. Still, as we contemplate the means of crossing intergalactic gulfs, we are haunted by the sheer immensity of the challenge. No method, be it wormholes, time dilation, warp bubbles, or gravitational slingshots, is free of consequence, complexity, or cost. Each demands its own brand of sacrifice of energy, of certainty, of time, or of return. And yet, in these ideas, we glimpse humanity's finest quality, its refusal to accept the horizon as final. Whether we travel by folding space or stretching time, we are ultimately chasing a reflection of ourselves across the stars, a desire to belong not only to Earth, but to the vast cathedral of the cosmos. And in doing so, we confront not just the physics of space, but the metaphysics of destiny. Will we one day ride the curvature of light, slingshot around stars, or surf the quantum ripples of the void? Or will we discover that the greatest journey was not one of motion, but of understanding, of reshaping our place in a universe that was never meant to be tamed, only touched, however briefly, by the reach of our imagination? The methods may differ, but the yearning remains unchanged, pulsing like a signal through the dark, the will to go further, to stretch the moment of now across the arc of eternity, and to find, in that crossing, not an escape from limits, but a celebration of them. Einstein-Rosen bridges and wormhole geometry. Long before wormholes entered the cultural imagination as portals for cosmic adventurers and science fiction epics, they emerged from the pages of sober physics whispers born not from fantasy, but from the pure language of Einstein's equations. It was 1935, and Albert Einstein, alongside his collaborator Nathan Rosen, was exploring the puzzling behavior of singularities and their implications in general relativity. Together, They proposed a mathematical model now known as the Einstein-Rosen bridge, a theoretical structure connecting two separate regions of space-time. At its heart was an effort to bypass the troublesome singularity at the core of the Schwarzschild black hole. By carefully gluing two solutions of the Schwarzschild metric back-to-back at their event horizons, they envisioned a tunnel, a bridge between distant points in the universe. But this solution, elegant as it was, harbored a fatal flaw. The throat of the bridge, the narrow passage that would connect one side to another, pinched off instantly. It collapsed too quickly for anything, not even light, to traverse. The Einstein-Rosen bridge was a fleeting illusion of connectivity, a non-traversable tunnel with no passageway for real matter. Yet the seed had been planted. Decades later, the idea would be reborn and reshaped in the minds of physicists who dared to imagine what it would take to hold such a tunnel open. In 1988, physicists Kip Thorne and Michael Morris approached the wormhole concept with an audacity matched only by their mathematical rigor. Where Einstein and Rosen had seen an ephemeral bridge, Morris and Thorne sought a traversable wormhole, one that a spacecraft or human traveler could pass through without being crushed by gravitational collapse. They constructed a theoretical metric that met this condition, but it came with an extraordinary requirement: the existence of exotic matter, a substance with negative energy density that violated known energy conditions. This strange form of matter would be needed to resist the immense inward pull of gravity and prop open the wormhole's throat. Unlike normal matter, which contributes positively to space-time curvature and thus reinforces gravitational collapse, exotic matter could curve space-time in the opposite direction, pushing outward where gravity pulls inward. It was not enough to merely imagine a tunnel. One had to devise the scaffolding that would keep it stable against the universe's relentless desire for equilibrium. In Morris and Thorne's traversable wormhole, geometry was not just a backdrop to physics, it was an active participant, a malleable conduit that could stretch and fold, provided nature could furnish the requisite materials. To fully appreciate how wormholes might function, one must venture deep into the mathematics of space-time metrics, particularly the shape function and the redshift function. Two central features that determine a wormhole's structure. The shape function, often denoted as BR8psi, dictates the spatial profile of the wormhole, defining how its geometry bends and curves as one moves along the radial coordinate. At the wormhole's narrowest point, called the throat, the shape function equals the radial coordinate BR0 x R0. This ensures that the tunnel opens at a finite, non-zero radius. But more importantly, for the geometry to be physically traversable, the derivative of the shape function must satisfy the flare-out condition essentially. The tunnel must widen as one moves away from the throat in either direction. This geometric requirement is directly tied to the violation of the null energy condition, a fundamental tenet in general relativity that normally prohibits negative energy densities. The redshift function, FR, governs the gravitational time dilation within the wormhole. If it diverges, it signals the presence of an event horizon, a barrier beyond which nothing can escape. To avoid this, FIFER must remain finite everywhere, ensuring a clear path for signals, particles, and hypothetical travelers to journey through the tunnel without becoming trapped in an eternal descent. Yet these clean mathematical functions conceal the deeper chaos and complexity of reality. The energy conditions they violate, particularly the null, weak, and strong energy conditions, are not just esoteric formulations. They are pillars upon which much of classical general relativity rests. Violating them introduces exotic behaviors, including the possibility of negative mass, backward time loops, and causality paradoxes. Still, physicists have not dismissed these violations outright. The Casimir effect, for instance, reveals that under certain quantum configurations, a negative energy density can arise between two closely spaced metal plates in a vacuum. While minuscule and confined to nanoscale distances, it offers a tantalizing glimpse into the physical plausibility of negative energy. Though scaling this effect up to the macroscopic realm of wormhole stabilization remains far beyond current technological reach. The very suggestion that quantum field effects might naturally produce such energies hints at a profound interplay between gravity and the quantum vacuum, a frontier where the shape of space might be engineered through fluctuations of fields invisible to the eye. As theoretical interest deepened, wormhole geometries grew more diverse, static. Spherically symmetric solutions gave way to more ambitious constructions, rotating wormholes, dynamic wormholes, and thin-shell wormholes patched together at discontinuities in spacetime. In rotating wormholes, angular momentum introduces frame-dragging effects that spiral spacetime itself, much like the ergosphere of a Kerr black hole. These structures can potentially allow closed timelike curves, meaning one could loop through the wormhole and arrive before they left, a concept that strains our intuitive grasp of time and causality. Dynamic wormholes, meanwhile, evolve with time expanding, contracting, or oscillating in response to external fields or internal pressures. These models often invoke scalar fields or phantom energy to fuel the exotic geometries. Then there are the thin-shell wormholes, born from the surgical joining of two separate spacetimes at a common boundary. These geometries are constructed using the Darmois-Israel formalism, a mathematical tool that allows the matching of metrics across hypersurfaces. By concentrating exotic matter at the shell, one can sidestep the need for negative energy throughout the entire spacetime, focusing it instead at a specific junction. This approach appeals to physicists seeking to minimize the weirdness required to make wormholes real. One of the more intriguing advancements in wormhole geometry involves the exploration of minimal violations, constructing models where the energy condition violations are infinitesimally small or localized to specific regions. Such models attempt to reconcile the mathematical requirements for wormholes with the physical constraints imposed by quantum field theory. They ask, can a wormhole exist with just enough exotic matter to do the job, but not so much as to contradict the rest of physics? The answer is not yet known, but numerical simulations suggest that fine-tuned configurations might allow for quasi-stable wormholes under certain theoretical scenarios. These constructions push the boundaries of semi-classical gravity, where Einstein's equations are modified by quantum stress energy contributions, and hint at the possibility that wormholes could be self-consistent solutions of a yet-to-be-discovered theory of quantum gravity. In this context, the spacetime fabric becomes more than a canvas. It becomes a dynamic participant in a cosmic dialogue between geometry, matter, and the quantum vacuum. And what of the connection between wormholes and black holes? At first glance, they appear to be mirror opposites. One traps information, the other could allow its escape. But their mathematical similarities are profound. The Einstein-Rosen bridge, after all, is the other side of the Schwarzschild black hole, a connection revealed only when the full extension of the metric is considered in Kruskal-Sekaris coordinates. In this extension, the black hole is not merely a one-way grave for matter, but part of a larger, connected spacetime that includes a white hole, a time-reversed black hole that ejects matter instead of consuming it. The full diagram reveals four distinct regions our universe: the black hole, the white hole, and a parallel universe. But no physical process allows traversal between them. The bridge is non-traversable because it closes off faster than light can cross. However, it offers an important philosophical insight. nature might permit connections between universes, albeit ones hidden behind the veil of causality. In more speculative frameworks, such as those inspired by quantum entanglement, it has been proposed that certain wormholes could be stabilized by quantum correlations across horizons. The ER-EPR conjecture, proposed by Juan Maldacena and Leonard Susskind, posits that Einstein-Rosen bridges ER and entangled particle pairs EPR are manifestations of the same underlying phenomenon. If true, this would imply that space-time connectivity and quantum entanglement are not separate ideas, but two sides of the same cosmic coin, a revelation that collapses the divide between geometry and information. Of course, with all such theoretical elegance comes profound uncertainty. No observational evidence has yet confirmed the existence of wormholes, traversable or otherwise. They remain ghosts in our equations, mathematical creatures constrained only by our creativity and consistency with known physics. Yet the very act of studying their geometry has yielded rich insights into the nature of gravity, space-time, and the deep structures of the cosmos. Whether wormholes are real or not, their mathematics demands that we stretch our understanding of what is possible. They compel us to ask, what would it mean to connect two galaxies by a tunnel? What would it take to walk through one side of the universe and emerge, blinking, on another shore? These are not idle dreams, but rigorous inquiries into the scaffolding of reality. Each shape function plotted, each energy inequality tested, each redshift profile constrained, becomes a stepping stone in our effort to reconcile the infinite with the reachable. And in doing so, we inch closer to understanding not just how to reach the stars, but how space and time themselves might open their secret doorways, if only we learn how to knock. The future of intergalactic travel, vision, and reality. There comes a point in every journey where the questions no longer belong solely to physics, nor to mathematics, nor to the boundaries of known engineering, but to the quiet corners of human longing. The final frontier is not just the edge of space, but the edge of our own imagination. If wormholes are real, if the fabric of space-time can be bent, folded, bridged, and traversed, then what are we to make of a universe so profoundly pliable to thought? For even the act of writing equations that bend the cosmos is an act of hope, a rebellion against limits, against silence, against extinction. And so we stand here, on the shore of a cosmic ocean, peering into the unknown with tools forged from logic and dreams, daring to ask not just how, but why. Why do we hunger to reach the stars? Why does the thought of a tunnel through space stir something ancient and infinite in us? Is it survival? Is it wonder? Or is it the simple desire not to be alone, not in the biological sense, but cosmologically, to know we are not trapped in our island of matter and time, and that some future mind might look back and understand that we tried, with trembling hands, to write ourselves into the deeper script of the universe, the Einstein-Rosen bridge. Born from a quest to unify particles and fields, has become a metaphor for transcendence itself, not only across galaxies, but across what we believe is possible. And that metaphor is evolving. As our telescopes peer farther and our equations dig deeper into the quantum foam, we begin to suspect that the universe is not static, but computational, that reality may be emergent, that entanglement is geometry, that information and gravity are dual faces of a deeper structure still unnamed. Wormholes, then, are no longer mere curiosities. They are nodes in a lattice of philosophical, scientific, and spiritual reckoning. If negative energy can be harnessed, if quantum fields can be sculpted, if space-time itself is programmable, then humanity must confront not just the technical question of can we, but the existential mirror of should we. what does it mean to sculpt a hole through the fabric of reality? Would such an act be a form of cosmic vandalism or a communion with the deeper symmetries of the multiverse? Might it alert intelligences far older and more patient than us? Or would it, perhaps, be like discovering fire again, in a darker and colder domain, reigniting the dream that intelligence is not a glitch in entropy, but an emergent phase of the universe awakening to itself? If so, then wormholes might be not just tunnels, but messages from the future to the past. From distant galaxies to the beating hearts of those who still dare to imagine the impossible. Even if we never build one, never find one, the pursuit transforms us. It elevates our thinking, unites physics and metaphysics, collapses the distance between poetry and cosmology. Wormholes teach us that reality may be more than what is visible, more than what is measurable. It may be navigable. And in that revelation lies both hope and humility. For all the redshift functions, Einstein tensors, and exotic matter requirements, the most powerful engine of intergalactic ambition may yet be the human soul's refusal to accept a quiet death under familiar stars. We dream of other skies because something in us is wired for wonder, for the crossing. This is not naivety. It is courage, the same courage that lifted our ancestors into sailboats at the edge of maps, that carved radio telescopes into the jungle, that etched Voyager's golden record in the hope that someone, somewhere, someday might hear the echo. In that same spirit, perhaps one day we will stand before the throat of a stable wormhole, not just to escape the confines of Earth, but to find new meanings, new beginnings. And perhaps we will leave messages behind us too, not instructions, but invitations, to love the cosmos as it is, to shape it only with reverence, to walk lightly, even when traveling faster than light. Until then, we will continue tracing the curvature of space in our minds, coding gravity into simulation, dreaming of bridges where none yet exist. Because sometimes, to be human is not merely to live, but to reach, to hope, and to carve a path through the silence. And in that quiet pursuit, across millions of light years, across equations and paradoxes, we may find not only the stars, but ourselves.
Time. It marches forward, unwavering and absolute, or so we thought. For centuries, humans perceived time as a rigid framework, ticking away at the same rate for everyone, everywhere. But what if I told you that time is not the steadfast constant we believed it to be? What if time, like a river, could speed up, slow down, or even bend? This is the mind-bending reality revealed by Albert Einstein's theory of relativity. Prepare to have your perception of time forever altered. Albert Einstein, a name synonymous with genius, revolutionized our understanding of the cosmos. His theory of relativity, presented in the early 20th century, shattered the illusion of time as an absolute entity. Einstein boldly declared that time is not absolute, but relative. Time, according to Einstein, is intertwined with space, forming a unified fabric called spacetime. This fabric is not rigid but flexible, capable of being warped and stretched by gravity and motion. One of the most intriguing consequences of Einstein's theory is time dilation. Simply put, time dilation means that time passes at different rates for observers who are moving relative to each other. The faster you move, the slower time passes for you relative to someone who is stationary. Imagine two identical clocks, one remaining on Earth and the other traveling at incredibly high speeds. When the traveling clock returns, it will show a slightly earlier time than the clock that remained on Earth. This is not a mechanical error, but a fundamental principle of the universe. The faster clock experienced time dilation, causing time to slow down relative to the stationary clock. Let's dive deeper into time dilation with a thought experiment. Imagine a train traveling at near the speed of light. Inside the train, a passenger shines a light upwards to the ceiling. From the passenger's perspective, the light travels in a straight line, bouncing directly back down. However, to an observer standing on the platform outside the train, the light beam appears to travel diagonally. This is because the train is moving horizontally while the light is traveling vertically. Since the speed of light is constant and the observer sees the light travel a longer distance, time itself must slow down on the train for the observer on the platform. Time dilation is not just a theoretical concept, it has real-world implications. One of the most striking examples is the Global Positioning System, or GPS. GPS satellites orbiting Earth rely on incredibly precise atomic clocks to provide accurate location data.
However, these satellites are also moving at high speeds, experiencing a slight time dilation effect.
To compensate for this, GPS satellites have their clocks adjusted slightly, taking into account the time dilation predicted by Einstein's theory.
Without this crucial adjustment, GPS navigation systems would be significantly inaccurate, highlighting the tangible impact of time dilation on our everyday lives.
Section 6. Time dilation and astronauts. A journey into the future. In this chapter, we delve into the fascinating concept of time dilation and its profound implications for astronauts venturing into the vast expanse of space. The effects of time dilation become even more pronounced in the realm of space travel. As spacecraft travel at incredible speeds, approaching the speed of light, time itself begins to behave differently.
Astronauts aboard the International Space Station, orbiting Earth at high speeds, experience a minuscule but measurable amount of time dilation. This phenomenon, though subtle, is a testament to the intricate relationship between velocity and time. Orbiting Earth at high speeds, these astronauts are part of a living experiment in the effects of time dilation. The faster they travel, the slower time moves for them compared to those on Earth. Experience a minuscule but measurable amount of time dilation. Upon returning to Earth, astronauts are technically a fraction of a second younger than they would have been had they remained on the planet. This tiny difference, though imperceptible in daily life, is a glimpse into the potential future of space travel. Astronauts are technically a fraction of a second younger than they would have been had they remained on the planet. This phenomenon, while small, opens the door to intriguing possibilities for long-duration space missions.
While the time difference experienced by astronauts on the ISS is small, future missions to distant stars and galaxies could result in significant time discrepancies. Imagine a journey to a distant star system where the effects of time dilation become much more pronounced. Future missions to distant stars and galaxies could result in significant time discrepancies. For astronauts traveling at near light speeds, time would slow down dramatically relative to those on Earth. This means that while only a few years might pass for the astronauts, decades or even centuries could elapse on Earth. For astronauts traveling at near light speeds, time would slow down dramatically relative to those on Earth. This phenomenon, known as time dilation, could have profound implications for the future of space exploration and our understanding of the universe. Time would slow down dramatically relative to those on Earth. This means that while only a few years might pass for the astronauts, decades or even centuries could elapse on Earth. The implications of this are staggering, as it challenges our very perception of time and reality. They could return to Earth after years of interstellar travel to find that decades or even centuries had passed. This concept, while theoretical, is grounded in the principles of Einstein's theory of relativity and has been observed in various experiments, to find that decades or even centuries had passed. The future of space travel holds many unknowns, but one thing is certain: the journey into the cosmos will forever alter our understanding of time, space, and our place in the universe. Section 7. Extreme time dilation, black holes. The ultimate cosmic time warpers are black holes. These enigmatic objects are formed when massive stars collapse under their own gravity, creating a point in space with an incredibly strong gravitational pull. These gravitational behemoths possess such immense gravity that they warp the fabric of space-time to an extreme degree. The closer you get to a black hole, the more intense this warping becomes, leading to some truly mind-bending phenomena.
Time near the event horizon, the point of no return for a black hole, slows down to a crawl relative to observers at a safe distance. This boundary marks the limit beyond which nothing, not even light, can escape the black hole's grasp. If you were to observe a spacecraft falling into a black hole, you would witness a bizarre spectacle. The spacecraft would seem to slow down as it approached the event horizon, appearing almost frozen in time. As the spacecraft approached the event horizon, it would appear to slow down, its movements becoming increasingly sluggish. This is due to the extreme time dilation caused by the black hole's immense gravitational field, its image red-shifting as time itself stretched to infinity. The light from the spacecraft would be stretched to longer wavelengths, making it appear redder and dimmer to an outside observer.
From the spacecraft's perspective, however, time would seem to flow normally, as if nothing unusual were happening. The crew inside would experience time at its usual pace, unaware of the dramatic time dilation occurring outside, a testament to the relative nature of time. This phenomenon highlights the fascinating and often counterintuitive effects of extreme gravity on the passage of time, reminding us of the complex and mysterious nature of our universe. Section 8. Time travel. A distant possibility. The concept of time dilation inevitably leads us to ponder the tantalizing possibility of time travel. Could we one day harness the power of time dilation to journey into the future or even the past?
While time travel remains firmly in the realm of science fiction, Einstein's theory does not explicitly rule it out. Some physicists speculate that wormholes, theoretical tunnels through space-time, could potentially act as shortcuts for time travel.
However, the existence of wormholes remains purely theoretical, and even if they do exist, navigating their unpredictable nature would be an immense challenge.
Section 9. Conclusion. Time is a river, not a straight line. Einstein's theory of relativity shattered our Newtonian view of time as an unwavering constant. Before Einstein, time was seen as a universal clock, ticking away uniformly for everyone, everywhere. This classical view was comforting in its simplicity, but it was also misleading. Einstein introduced the radical idea that time is not absolute. Instead, it is intertwined with the fabric of space itself, forming what we now call spacetime. We now know that time is a fluid and relative concept, influenced by gravity and motion. Imagine time as a river, its flow changing speed and direction depending on the landscape it traverses. In the presence of massive objects like planets and stars, the river of time bends and slows. This phenomenon, known as time dilation, means that time can pass at different rates depending on where you are and how fast you're moving. Time dilation, a consequence of this revolutionary theory, has profound implications for our understanding of the cosmos and our place within it. For instance, astronauts aboard the International Space Station experience time slightly slower than we do on Earth. This effect, though minuscule, is measurable and has been confirmed through numerous experiments. It challenges our intuitive understanding of time and forces us to rethink our place in the universe. From GPS satellites to the journeys of astronauts, time dilation is not just a theoretical curiosity, it is a fundamental aspect of our universe. GPS systems, which we rely on daily for navigation, must account for time dilation to provide accurate positioning. Without these corrections, the system would quickly become unreliable. This real-world application underscores the importance of understanding time as a dynamic and relative entity. As we continue to explore the cosmos and unravel its mysteries, our understanding of time will undoubtedly continue to evolve, leading to even more mind-bending discoveries. Each new mission, each new observation, adds another piece to the puzzle. The more we learn, the more we realize how much we have yet to understand. The journey of discovery is ongoing, and the river of time flows ever onward, carrying us toward new horizons. Ultimately, time is not a straight line but a winding river, its flow forever intertwined with the fabric of space-time. Just as a river can carve through mountains and shape the land, the flow of time shapes our universe and our understanding of it. Embracing this fluid and dynamic nature of time opens up endless possibilities for exploration and discovery, reminding us that the journey is just as important as the destination. The concept of time travel has captivated the human imagination for centuries. From ancient myths to modern science fiction, The idea of moving through time has always fascinated us. We see it in literature, film, and our wildest dreams. The notion of stepping into a time machine and visiting different eras is a recurring theme that never loses its charm. The ability to journey through time, to witness historical events, or to get a glimpse of the future holds an irresistible allure. Imagine standing on the deck of the Titanic or witnessing the first moon landing. This desire to explore the unknown, to change the past, or to peek into the future is a testament to our innate curiosity about the nature of time itself. It's a reflection of our deepest desires to understand our origins and destiny. But is time travel merely a product of our imagination, or could it one day be within the realm of possibility? Could we ever build a machine that transcends the boundaries of time? Science fiction has explored the possibilities and consequences of time travel extensively. These stories stretch our minds and challenge our understanding of reality. From H.G. Wells' The Time Machine to the intricacies of the Back to the Future trilogy, we have been both entertained and challenged by the implications of manipulating time. These narratives invite us to ponder the ethical and moral dilemmas of altering history. These stories often serve as cautionary tales, highlighting the potential paradoxes and unintended consequences that could arise from tampering with the fabric of time. They remind us that with great power comes great responsibility. While time travel remains a theoretical concept, the pursuit of understanding its possibilities pushes the boundaries of our scientific knowledge. Researchers continue to explore the mysteries of time and space, driven by the hope of one day unlocking its secrets. It compels us to ask fundamental questions about the nature of the universe, the nature of causality, and our place within the grand tapestry of time. The allure of time travel is not just about the destination, but the journey of discovery itself. Albert Einstein, the renowned physicist, revolutionized our understanding of space and time with his groundbreaking theory of relativity. His insights have fundamentally changed the way we perceive the universe and our place within it. His work laid the foundation for the theoretical possibility of time travel, suggesting that time is not absolute but is relative to the observer's frame of reference. This was a radical departure from the Newtonian view of time as a constant, unchanging entity. Einstein's equations showed that time can be stretched and compressed, a phenomenon known as time dilation. This means that time can flow at different rates depending on the speed at which an object is moving. One of the most intriguing aspects of relativity is the concept of time dilation, which states that time passes slower for objects moving at high speeds relative to a stationary observer. This has profound implications for our understanding of time and space. This effect becomes more pronounced as an object approaches the speed of light. The closer an object gets to this ultimate speed limit, the more time slows down for it. For example, if one were to travel in a spaceship at a significant fraction of the speed of light, time would pass slower for them relative to someone on Earth. This is not just a theoretical concept, but a real effect predicted by Einstein's equations. This means that upon returning from their journey, the traveler would have aged less than their Earth-bound counterparts, essentially traveling into the future. This fascinating idea has captured the imagination of scientists and science fiction writers alike. While achieving such speeds is currently beyond our technological capabilities, the concept of time dilation has been experimentally verified using atomic clocks. These experiments have shown that time does indeed pass at different rates depending on the relative speeds of the clocks. Another intriguing concept that emerges from Einstein's equations is the possibility of wormholes, theoretical tunnels that connect two distant points in space-time. Imagine folding a piece of paper in half and poking a hole through it. That's a simplified visualization of a wormhole. These cosmic shortcuts could potentially allow for travel across vast distances, even between different points in time. However, the existence of wormholes remains purely theoretical. One of the major challenges lies in the fact that they are incredibly unstable and would require exotic matter with negative mass energy density to hold them open. This type of matter, while theoretically possible, has never been observed. Despite these challenges, the concept of wormholes continues to fascinate physicists and science fiction enthusiasts alike. If we could somehow harness the power of wormholes, we might be able to unlock the secrets of time travel and explore the universe in ways we never thought possible. Beyond wormholes, another theoretical construct proposed by physicists is the cosmic string. These are hypothetical, one-dimensional defects in space-time, remnants of the early universe's formation. Imagine them as incredibly thin, extremely dense threads of energy stretching across the cosmos. While their existence is yet to be confirmed, some theories suggest that cosmic strings could potentially be manipulated to create closed, time-like curves, essentially loops in space-time that could facilitate time travel. The immense gravitational pull of these cosmic strings could, in theory, be harnessed to warp space-time sufficiently to create closed, time-like curves. A spacecraft, for instance, could theoretically travel along such a curve, effectively traveling back in time. However, the challenges associated with manipulating cosmic strings are even more daunting than those posed by wormholes. Not only do we need to confirm their existence, but we also need to develop a deep understanding of their properties and the technology to harness their immense energy. While the concepts of wormholes, cosmic strings, and time dilation offer tantalizing possibilities for time travel is riddled with paradoxes that challenge our understanding of causality and the very fabric of reality itself. The most famous of these is the grandfather paradox, a thought experiment that has puzzled scientists and philosophers alike. It poses a rather disturbing question. What would happen if you traveled back in time and accidentally killed your grandfather before your parent was born? Would you cease to exist, vanishing from the timeline as if you were never born? Or would the universe unravel, unable to reconcile the paradox, leading to a cosmic disturbance? This thought experiment highlights the potential contradictions inherent in time travel, making it a fascinating yet perplexing topic. Several solutions have been proposed to address the grandfather paradox, each with its own intriguing implications. One possibility is the existence of parallel universes or alternate timelines, where each action creates a new branch of reality. Perhaps traveling back in time transports you to a parallel universe where you can interact with the past without altering your original timeline, thus avoiding any paradox. Another solution is the Novikov self-consistency principle, a theory that offers a different approach to resolving these paradoxes. This principle posits that if you were to travel back in time, something would always prevent you from changing the past in a way that would create a paradox, ensuring that events remain consistent. Essentially, the universe has a way of self-correcting to maintain consistency, preserving the balance and order of the cosmos. Even if we could overcome the paradoxes associated with time travel, the practical challenges are immense. Creating wormholes or manipulating cosmic strings would require unimaginable amounts of energy, far beyond our current capabilities. We would need to develop technologies that can harness and control these energies, a feat that currently lies firmly in the realm of science fiction. Furthermore, the stability of wormholes or time-like curves created by cosmic strings is questionable. Maintaining a stable passage through time would likely require a mastery of exotic matter and its properties. We are still a long way from fully understanding these theoretical concepts, let alone manipulating them to our advantage. While time travel remains a distant dream, the pursuit of understanding its possibilities continues to drive scientific inquiry and technological advancement. While we may not be hopping into time machines just yet, we do have concrete evidence of time dilation, one of the intriguing consequences of Einstein's relativity. Experiments with atomic clocks have demonstrated that time does indeed pass slower at higher speeds. For example, atomic clocks flown on jets have shown a minuscule but measurable time difference compared to their Earth-bound counterparts. While this time difference is incredibly small, it provides tangible proof that time is not absolute, but is influenced by speed. This subtle manipulation of time, while not quite time travel in the traditional sense, offers a glimpse into the mind-bending possibilities that govern our universe. Time, as a concept, continues to fascinate and baffle physicists and philosophers alike. Is it a fundamental aspect of the universe, or is it an emergent property arising from something more fundamental? Does time flow in one direction, or is our perception of its passage merely an illusion? These questions lie at the heart of our quest to understand the nature of reality. The pursuit of time travel, whether it remains a distant dream or becomes a future reality, compels us to confront these fundamental questions and to expand the boundaries of our knowledge. While the practicalities of time travel remain firmly in the realm of science fiction, The pursuit of understanding its possibilities continues to inspire scientific exploration and technological innovation. The quest to unravel the mysteries of time pushes us to ask fundamental questions about the universe and our place within it. Who knows what breakthroughs await us in the future? Perhaps one day, armed with a deeper understanding of the cosmos, we will unlock the secrets of time travel and embark on journeys through the annals of history or into the uncharted territories of the future. Until then, the dream of time travel will continue to fuel our imaginations and inspire us to push the boundaries of human ingenuity.